Alright, today we're going to study special kinds of maps between groups called homomorphisms. Alright, suppose we have two groups, G and H, and suppose I want to map between them. I.e., suppose I want to have a function whose inputs are in G and whose outputs are in H. Now we can do this, but it's more interesting if we add an extra property to this function between groups, and that is this. Suppose phi of A times B for any A and B in the group G. So this is the multiplication operation in G. Just to be sure, I'll write G asterisk and H little tensor product symbol. So this is the operation in H, this is the operation in G. So now, if phi of A asterisk B is equal to phi of A times, now the H multiplication, phi of B, for all A and B in the domain G, then phi is said to be operation preserving. Right? So a multiplication in G is equivalent to a multiplication in H. That's what this is saying. In other words, it preserves structure. Now an operation preserving map between two groups is called a group homomorphism. So phi is said to be a homomorphism of G into H. Now, just as there are different kinds of maps, there are different kinds of homomorphisms. So if we just have, we'll say phi is just a homomorphism to begin with. So we assume this. Now, if on top of being a homomorphism, phi is 1 to 1, we're going to call phi a monomorphism. Likewise, if phi is onto or surjective, then we're going to call phi an epimorphism. Right? Mono, 1, epi, onto. Now a homomorphism which is both onto and 1 to 1, in other words, both surjective and injective in set theory terms, or in our current terms, both an epimorphism and a monomorphism, then we call phi a, if it's bijective, we call it an isomorphism. Likewise, if the group H is equal to the group G, in other words, if phi is a function from G to G, and phi is a homomorphism, then we're going to call phi an endomorphism. And if phi is an endomorphism, which is also an isomorphism, it has another special name, which we already know. So these give birth to an automorphism. Told you about the automorphism group before. So an automorphism is just an isomorphism of a group onto itself. Alright, as our first homomorphism, let's look at the map phi from the additive integers to the additive even integers, given simply by phi of m is equal to 2m. Alright, so obviously for any input in the integers, the output is going to be in the even integers. So what we're concerned with here is proving that phi is an operation preserving map. Alright, so to do that, we would say, what is phi of m plus n for arbitrary m and n in the integers? Well, phi of m plus n is just going to be equal to 2 times m plus n, which in this case is equal to 2m plus 2n, and this is going to be equal to phi of m plus phi of n. Of course, I'm using additive notation here once again, and also we have a special case. It's very simple because both sets actually have the same operation, so we don't even have to really concern ourselves with that. But in general, that's not the case. Alright, so here we have the groups S2 and S3, and last time I told you that S2 is a subgroup of S3. Now here, the way I've labeled this is that sigma 2, 3 is the mapping from a set of 3 elements to itself such that we switch 2 and 3. So 2 goes to 3 and 3 goes to 2, while 1 must go to itself. Likewise, sigma 1, 2 is going to be switch 1 and 2. Sigma 1, 3 is going to be switch 1 and 3. I have pi r as the cyclic permutation where each element goes 1 to the right. 1 goes to 2, 2 goes to 3, 3 goes to 1. And pi l as the sort of left permutation here where we go 3 to 2, 2 to 1, 1 to 3. And then of course there's the identity mapping. And I claim that this is S3, and then S2, which we've talked about a few times now, is just the identity element and switching elements 1 and 2. Alright, now consider the map, we'll call it F, from S2 to S3, which is given precisely by sending the identity to the identity and the permutation of 1 and 2 to, let's say, the switching of 1 and 3 instead. I claim this is a homomorphism. Why? Suppose we have some product. So the only two, well, we can have 3 products here. So we can have sigma 1, 2 with the identity, we can, which is in this case, because all elements commute with the identity, equal to sigma 1, 2. We could have the identity with the identity, which is clearly just the identity. And we could have sigma 1, 2, sigma 1, 2. But if you switch elements 1 and 2 twice, it's just the identity, right? So this is equal to the identity. So the question is, does our function f preserve products? So if we take f of sigma 1 times the identity, which is the same as just taking f of sigma 1, 2, this is going to be equal to sigma 1, 3, right? Sigma 1, 3. But this is equal to sigma 1, 3 times the identity in S3, and so this is going to be f of sigma 1, 2 times f of the identity in S2. So it preserves that product. By the same argument, these two products are preserved. Notice that switching 1 and 3 and then switching them again is going to be the same in this group as switching 1 and 2, right, with this group. So that we get our map F is operation preserving, and so it's a homomorphism. Alright, now there are a couple trivial homomorphisms which you should know about. Namely, the one which sends all elements to the identity. So suppose we have some group G, and we have a function from G to just the identity element of G, so that we have phi of G is equal to E sub G for all elements of the group G. Alright, is this a homomorphism? Well, let A and B be arbitrary elements of the group G, and then we know this. AB is going to be another element in the group G because G is a group, right? It's closed under products, but we said that for all G we're mapping it to the identity. So clearly the element AB also gets mapped to the identity. So phi of AB is equal to E times E, right? The identity times the identity is still just the identity. But since A and B each individually get mapped to the identity, this is no different than phi of A times phi of B. And so we see that phi is an operation-preserving map, and thus a homomorphism. Now, likewise, there's going to be another trivial homomorphism. That's going to be the identity homomorphism, right? The identity homomorphism is just the homomorphism which sends every element in a group to itself, right? Under the same operation. So it is not only going to be a homomorphism, it's clearly going to be an isomorphism. All right, so now a few important theorems. All right, so let's prove some basic properties about homomorphisms. First of all, okay, so if phi is a group homomorphism of G into H, then it fixes the identity. In other words, the image of the group identity in G is going to be the group identity in H. How do we show this? All right, so let's consider the product phi of E sub G times A for arbitrary A in the group G, right? This is going to be equal to phi of A times E sub G because every element is going to commute with the identity element. But now we know that because phi is operation preserving, it's assumed to be that this is equal to phi of E sub G times phi of A. And this, likewise, is going to be phi of A times phi of E sub G. But since E sub G times A is just A, this has to be equal to phi of A. Likewise, this has to be equal to phi of A. Now for what elements x in the group H are we going to have xa is equal to ax is equal to A? Well, that's only going to be the identity element. In fact, this is the definition of the identity element. Specifically the identity in the image of the map, not necessarily the whole group, but because identities are unique, it must also be the identity in H. Thus, phi of E sub G is equal to E sub H. Alright, now for the second part. Let's consider the mapping phi of A inverse. Well, this is going to be equal to phi of the identity in G for any elements A and G. But it's also going to be equal to, by operation preservation here, phi of A times phi of A inverse. Now since we know that E sub G is mapped by phi to E sub H, then we can say that this is equal to the identity in the group H. Likewise, if we do this in the reverse order, we find that it must be true that the product in this order is equal to E sub H. But if this is true for all A in the group G, then it must also be true for all phi of A in the image of G under phi. Thus, at least in the image of G, these are inverses of each other. And because inverses are unique in the whole group, not just in the subgroup, we're going to conclude that these are inverse elements in the group H. Thus, phi of A inverse must be equal to phi of A inverse. Alright, now the kernel of a homomorphism. If we have a homomorphism from G to H, then the kernel of the homomorphism phi is going to be the set of all elements in the domain group G such that phi of G is going to be equal to the identity in the group H. If you want to think of this additively, it's the set of all elements which map to 0. Or multiplicatively, the set of all elements which map to 1. Alright, now an important theorem. If phi is a group homomorphism of G into H, then the kernel of the map phi is a subgroup of the domain G. Alright, so for all A and B in the kernel of the homomorphism phi, we're going to have that phi of AB inverse is going to be equal to phi of A times phi of B inverse, because it's a homomorphism, so it preserves the operation. And we just proved that the homomorphic image of an inverse element is equal to the inverse of the homomorphic image, right? However, by assumption, A and B are both in the kernel, which means the phi of A is equal to the identity in the group H, and likewise with B, so that we have E sub H times E sub H inverse. And of course, the inverse of the identity is just the identity, times the identity is going to be the identity. Thus, the arbitrary element AB inverse is in the kernel of phi, and by the subgroup test, we conclude that the kernel is a subgroup of the domain G. Alright, I expect you to already know what the image of a set under a map is, right? The set of all elements which get mapped to. So if we consider not the kernel, but now the image of the group homomorphism phi, and so if phi goes from G to H, they're groups, right, and it's a homomorphism, and I claim the image of the map is a subgroup of the codomain H. Alright, now for all elements A and B in the image of G under the homomorphism phi, we have that there exist values, I'll call them capital A and capital B, in the group G. This is just the definition of an image set such that phi of little a is big A, or sorry, other way around, phi of big A is little a, and phi of big B is little b. Alright, so now we apply the subgroup test. So we take our two arbitrary elements that live in the image of phi, and we multiply them AB inverse, right? And then we say, well, A is really phi of big A, right? And B inverse is really the inverse of phi of B. Well, by the theorem we just proved a few minutes ago, this is equal to phi of A times phi of B inverse, and then by operation preservation, I don't know. This is phi of AB inverse. But since the group G is closed under multiplication, right, we have that AB inverse must be another element in G, so there exists an element, namely capital A times capital B inverse, which maps to little a B inverse, so that this element must also be in the image of phi, and we have that it passes the subgroup test. Image of phi is indeed a subgroup of H. Alright, just as an aside, the image of a set under a function, well, we normally just call that the image, but when that function is a homomorphism between groups, we call it the homomorphic image. Alright, another cool theorem. If phi is a group homomorphism from the group G to the group H, and the kernel of phi is just the identity element in the group G, then phi is injective. In other words, phi is a one-to-one mapping. Alright, so to show that it's injective, we have to show that for arbitrary elements A and B in the group G, that we have phi of A equals phi of B implies that A equals B. Can we show this? Yes, we can. First, assume for some A and B in the group G that phi of A is equal to phi of B. Now consider the following. Phi of A times B inverse, which is an element in G by closure and such, is going to be equal to, because phi is a homomorphism, it's going to be equal to phi of A times phi of B inverse, which is phi of B inverse, right? But since phi of B is equal to phi of A, this is equal to phi of A times phi of A inverse. But by definition, this is just the identity in H. But anything which maps to the identity in H must be in the kernel of phi. That means that AB inverse is in the kernel of phi. But the kernel of phi has only one element, so that A times B inverse must be equal to the identity in G. Likewise, we can do the same logical chain with B inverse A instead of A B inverse, so that A B inverse has to be equal to B inverse A has to be equal to the identity element in the group G. Now this can only mean one thing, that B has to be equal to A by the definition of inverses. So we have that phi of A is equal to phi of B for a group homomorphism from G to H implies that B is equal to A, together with the fact that the kernel of the group homomorphism is just the identity element. Alright, so here's a fun theorem. If alpha from G to H and beta from H to K are group homomorphisms, then there exists a third group homomorphism, gamma from G to K. If I were to draw this as a picture, it would look like, suppose we have G here, H here, and K here, and alpha is a homomorphism from G to H, beta is going to be a homomorphism from H to K, and likewise we have that there must then exist a third homomorphism completing the triangle. By the way, diagrams of this nature are called commutative diagrams. Alright, first we want to make sure that there exists such a mapping from G to K. It hasn't come up yet that our homomorphisms fail to even be a mapping to begin with, but in this case it might. So I want to draw attention to the fact that because alpha and beta are assumed to be group homomorphisms, they are more primitively mappings. That means that for all G in the group G, or just viewed as a set, there exists an H in the set H such that alpha of G is equal to H. Likewise, we're going to have a corresponding property that there exists a K in the set K for every H in H such that B of H is equal to K. This is the definition of functions. Now I'm going to draw a picture for you. So here is our set G, here is our set H, and here is our set K. Now I'm assuming that for every element in G, it's going to get mapped to something in H, but not necessarily all of H. If it is all of H, then the mapping is onto, right? So this is going to be alpha, and then beta is going to be defined for all of H, so including the white area, onto some subset of K, right? So beta is actually not going to be defined as a function if we only consider the image of alpha as its domain. So what we want to do is create a second map, and this is a bit of a technicality, but we're going to call B sub alpha the restriction of beta to alpha, to the image of alpha, my bad. So we want to consider, that is, beta alpha is going to be precisely that function for which beta alpha of H is equal to beta of H for all H in the image of alpha, but it's not going to be defined outside of that. It's going to be precisely beta restricted to this domain, the image of alpha, or the image of G under alpha, rather. If we do this, then we're going to define our third map in the following way. That for all elements G in the group G, gamma of G we're going to define to be the composed map beta sub alpha, beta restricted to the image of alpha, composed with alpha of G. Now by the definition of functions, this is going to be equal to beta sub alpha of G. But since by the definition of function, we said alpha is a function, for every G there's going to exist H in the group H such that alpha of G is H, then we're just going to substitute that H value into here. And likewise for every element of the domain H, beta has an output in K. So what our restriction does is that for every H in the image of alpha, beta sub alpha has an output in K. And we will just call it K. And thus, because this is a function and this is a function, and because the restriction of beta to the image of alpha is a function, we have that for all G in the group G, there exists K in the set or group K such that G maps to K under gamma. Now we need to show that gamma is operation preserving. Well, suppose we have two elements, A and B, in the group G. Then gamma of the product A times B, which is another element in G, and we know that this is going to be defined for all elements in G, so gamma of A times B is going to be equal to, by definition, the composed map B restricted to the image of alpha composed with alpha of AB, and by the rules of functions, this is equal to beta alpha of AB, right? And we know that alpha of AB is going to be equal to alpha of A times alpha of B, because alpha was assumed to be a group homomorphism, so it is operation preserving. Moreover, we proved before that the image of a group under a group homomorphism, namely in the image of alpha here, is a subgroup of the group H. Now, since the image of alpha is going to be a subgroup of H, this means that alpha of A times alpha of B is going to be another element in the image under alpha, which means particularly it is in the domain of beta restricted to the image of alpha. Moreover, we said that beta and beta sub alpha coincide on the image under alpha, which means that beta sub alpha is also going to be operation preserving, and we have beta sub alpha of A times beta sub alpha of B. And by the definition of functions and function composition, this is just going to be beta sub alpha composed with alpha of A times beta sub alpha composed with alpha of B. But this is our definition of gamma, so that this is equal to gamma of A times gamma of B. And thus we see that gamma is indeed operation preserving, and since it is a mapping from the group G to the group K, as we showed a second ago, and it is operation preserving as well, gamma is going to be a group homomorphism from G to K. In particular, I'd like to draw your attention to the case where the mapping alpha is onto. In other words, for every element in the group H, there is an element in the group G mapping to that element in H. In this case, we don't have to restrict the mapping beta to the image of alpha, we can just take its domain to be H. You can also prove that if both alpha and beta are onto homomorphisms or epimorphisms, then the induced homomorphism gamma will also be an epimorphism. Likewise, if they're both 1-to-1, gamma will be 1-to-1. And if they are both isomorphisms, then gamma will be an isomorphism as well. As a special case, take all three groups to be the same group, G, and take the mappings to be isomorphisms. This means that if we have an isomorphism from G to itself, and say another isomorphism from G to itself, then their composition is going to be an isomorphism from G to itself. The set of all automorphisms from G to G must therefore form a group. And this is what we conventionally mean by what I introduced to you before, the automorphism group of a group G, the set of all automorphisms from G to G. If we're instead talking about, say, the set of all bijections from a set of n elements to itself, we will no longer call this automorphisms. We will call this the symmetric group on n symbols. However, I really would like to emphasize that these are essentially the same thing. Only this is automorphisms on a set, if you will, or just bijections on a set, where these are automorphisms on a group, so that they have the extra property that they are operation preserving. Alright, suppose we have two functions of this form, where a1d1 minus b1c1, and likewise here, is non-zero. Now we want to consider such linear fractional transformations under the operation of function composition, where z is our independent variable. So let's plug this into this and see what happens. a1 times a2z plus b2 all over c2z plus d2 plus b1 all over c1 times a2z plus b2 all over c2z plus d2 plus d1. Alright, now let's multiply by c2z plus d2 all over c2z plus d2. What are we going to get? And so it's a little bit messy, but what you'll notice is that we have a constant times z plus a constant divided by a constant times z plus a constant. This is the exact same form we originally had. So what we get is that these linear fractional transformations under the operation of composition of functions are closed. Similarly, you can show that the binary operation is associative, that they have an identity and inverses, and thus form a group under function composition. Now I would like to consider a homomorphism. From these linear fractional transformations, I will just call them L. So a function phi from L to the general linear group of 2 with real coefficients. If I didn't say this before, we are considering linear fractional transformations with real numbers in them. Alright, and we're going to define our function by phi of az plus b all over cz plus d is equal to the matrix A times, or A, B, C, and D. And before, we imposed the restriction that AD minus BC is not 0. Thus, we are going to have that this is a member of the general linear group. So for every element in here, there is an output in here. So it is a mapping. Well, is it a homomorphism? Well, we have to show that it preserves products. Now this was the linear fractional transformation we got before when we composed the two. We noticed that if we now map this via the homomorphism, or what we're claiming as a homomorphism, then these are going to be our 4 matrix entries. But rather amazingly, this is exactly the matrix you would get if you multiplied 2 matrices like this under conventional matrix multiplication. So it is true that it's going to preserve products, and this is a great example of a homomorphism where the two products are absolutely wildly different, but it still preserves operations, right? Here we have function composition, and here we have matrix multiplication. The two operations could not be any more different, but this homomorphism preserves it. Consider the map gamma of M is equal to the determinant of M. Well, for precisely because determinant of a product Mn is equal to the determinant of M, times the determinant of n, we have that the determinant is operation preserving. Matrix multiplication corresponds to just normal multiplication here, so that it is operation preserving and hence a homomorphism from the general linear group to the multiplicative real numbers without zero. Now, as a cute application of our universal mapping property, since we have a homomorphism from the linear fractional transformations such that AD minus BC is non-zero to the general linear group, and then a homomorphism from the general linear group to the multiplicative real numbers without zero, where this is the determinant map, then there must exist an induced homomorphism, we'll just call it gamma, from the linear fractional transformations to the multiplicative real numbers without zero. And it is given precisely by the composition of determinant of phi.